I will be presenting to you Credence. Here in this work, we show the benefits of augmenting data center switch buffer sharing with machine learned predictions. This is a joint work with Maciej and Stefan. We are from the Intelligent Networks group from TU Berlin. I will not bore you with a lot of technical details. Let's start with the game first. There is an event venue that's just like this with 4 entry gates, 4 exit gates. The venue is slightly different than this. It only has a capacity limit of 6 people. It also has a bouncer to control the entry into the venue. Let's see how the game works. People come in 1 at a time from each gate, and they have a specific exit in mind when they arrive. Let's see how this works. All of them go to exit number 1. They queue up there, and only one person can exit at each point in time. When somebody goes out, we get a score of 1. Let's continue the game. More people arrive. This time, 3 people go to the exit 1. The last one, unfortunately, cannot fit in the venue, so they get rejected. 1 goes out, and the score is +1, a total of 2. More people come in. This time, all of them go to different exits. 3 get rejected because of capacity limits. Only 1 goes out, and we have a score of 3, and this repeats again and again. As we see, for 20 arrivals, we only have a score of 5. This was a pretty bad game. Let's see if we can do anything better just for the same arrival sequence. 4 come in. Let's take all of them this time. 1 goes out. This time, let's do something different. Reject all those that go to the first exit. We take the one that goes to the exit number 3. This is still within the capacity limit. Let's see if this allows us to increase the score. 2 go out this time. The score is 3. More arrivals come in. All of them fit in again. 4 go out, and this repeats over and over again. As you see, this time our score is 3 times better than what we did before. This very interesting game essentially shows how admission control algorithms can either improve throughput or severely impact throughput. And this is exactly the buffer sharing problem in data centers. A network switch has input ports, output ports, and they all share a common buffer space. A buffer sharing algorithm decides which packet to buffer and which packet is rejected. Buffer sharing is indeed an emerging critical problem in data centers, and this is mainly because traffic is bursty, and this requires certain amount of buffering in the network to avoid packet losses. Furthermore, traffic has very stringent performance requirements, but buffer sizes are unable to scale up proportional to the capacity increases. Essentially, what this means is the amount of buffer available per unit capacity is gradually decreasing over time. As a result, buffer sharing algorithm can severely impact the end-to-end performance in a data center, for instance, in terms of flow completion times. In this work, we take an online perspective to this problem. Our goal is to maximize the number of transmitted packets, which is essentially a throughput maximization problem. An online algorithm has no prior knowledge about the future. It takes spontaneous decisions upon every packet arrival, either accept or drop. Offline optimal algorithm, this has the prior knowledge of the entire packet arrival sequence. It computes the optimal solution for this particular sequence, and we call such an algorithm opt. This allows us to compare our online algorithms against an optimal solution. To do this, we use the metric called competitive ratio. Essentially, an algorithm is C competitive if the optimal algorithm for this particular packet arrival sequence transmits no more than C times that of alg. Here, C would be the competitive ratio. 2 types of algorithms exist in the literature. One is drop tail, and the other is push out. Drop tail is very simple. A packet comes in, and the drop tail algorithm can only accept or drop. If a packet is accepted, we cannot do anything more than just transmitting the packet from the buffer. Push-out algorithms, on the other hand, have the superpower to accept the packet, but later on push out the packet if needed. So they can accept all the incoming packet arrivals, but when needed, they can push out some packets to accommodate other packets. Unfortunately, push-out is not supported in hardware, but drop-tail is nearly supported in all commodity switches. In terms of competitive ratio, starting from ratio of 1, which is the optimal throughput, and as the competitive ratio increases, throughput lowers. All the known drop-tail algorithms, unfortunately, have a very high competitive ratio. On the other hand, a simple push-out algorithm has almost close to optimal performance. As we saw before, drop-tail is the only supported operation in hardware, and we cannot support push-out in hardware. Our main pursuit in this work is whether we can unlock some of this gap between the performance of existing drop-tail algorithms and the push-out's performance. To do this, to answer this, we first look into the limitations of existing drop-tail algorithms. They have two distinct types of problems. The first is they experience proactive unnecessary drops, which leads to throughput loss, and that affects the competitive ratio. What this means is that they try to over-provision for the future packet arrivals, and this leads to unnecessary drops, and these could have been avoided if the future was actually known ahead of time. In contrast to this, certain algorithms experience reactive avoidable drops, which again leads to throughput loss. Here, the algorithm under-provisions for the future, accepts too many packets, and these packet drops could have been avoided if the future was known. The short answer is that, unfortunately, we cannot unlock any of the space between the existing algorithms and the push-out. There is a well-known strict lower bound for drop-tail's performance in the literature. So given that, we still have some hope that predictions might improve buffer sharing performance. The idea would be to predict the actions of a push-out algorithm, and then augment a drop-tail algorithm with these predictions. This way, the algorithm can peek into a tiny window of the future, and the hope would be that we might be able to reduce the competitive ratio of drop-tail algorithms. Let's see if this works. A naive approach would be to just predict the LQD here is the longest queue drop, which is the push-out algorithm. We predict the actions of a push-out algorithm and do exactly what the predictions say. The catch is that predictions might be imperfect. The predictions might tell us exactly what the push-out algorithm is doing or the complete opposite. So in the paper, we show very interesting cases where false positive errors can actually lead to starvation. The naive case would be every prediction is a drop, so we keep dropping every incoming packet. There's another interesting case where false positive errors can hurt throughput forever, even a single false positive error. We discuss these details in the paper. For the interest of time, I'll leave these details for now. So within this framework, our goals are consistency, that is to perform close to what a push-out algorithm could do if the predictions are perfect. We also want robustness, which is even when the predictions are arbitrarily worse, we still want to perform as good as existing algorithms. Further, we want smoothness, that is a tiny error in predictions shouldn't lead to a drastic change in performance. So can we really unlock this space? No, but only without predictions. It turns out that we can really unlock the entire spectrum from the optimal performance all the way towards the existing algorithm's performance. And the performance we obtain by augmenting with predictions really depends on the accuracy of these predictions. We designed Credence. This is the first drop-tail buffer sharing algorithm that is augmented with predictions. It's a threshold-based scheme, which is quite similar to existing algorithms. It achieves all the three goals we discussed before: consistency, robustness, and smoothness. Credence assigns thresholds per queue, which is similar to existing algorithms, but the way we use the thresholds is much more different. The interesting idea here is that the thresholds implement the push-out algorithm. This doesn't require push-out operation in hardware, but all we need is an arithmetic push-out operation. So push-out here only means plus and minus a packet size. So based on these thresholds, a packet is immediately rejected if the queue length is greater than the threshold. If it is lower, only then we take a prediction and do exactly what the predictions say. This enables us to tackle false negative errors. Essentially, this prevents us to take the proper amount of packets and prevents accepting too many packets into the buffer. For example, if the predictions are all accept, thresholds still prevent us from accepting too many packets into the buffer. Further, we use a safeguard condition to tackle false positive errors. Here, this is only when longest queue is within a certain queue size. This prevents us from starvation, essentially not dropping too many packets. There are furthermore interesting details in the paper from competitive analysis perspective, the theoretical bounds of our algorithm, and many more interesting parts. Please have a look at the paper for these details. Finally, we evaluate this algorithm using packet-level simulations in NS3. We use a topology of 256 servers, 4 spine switches, and 16 TOR switches. We use 10 Gbps NICs at each server. Switches implement shared buffer, and within this shared buffer architecture, we use different algorithms and compare Credence. In particular, we use a random forest model for predictions in the case of Credence. Let's see how this works out in reality. Here on the x-axis is the burst size in terms of incas that were generated in the workload. As the burst size increases, we are looking at how the flow completion time slowdown affects the burst, changes in terms of burst size. The algorithms we compare are the previous work's ABM, dynamic thresholds, which is the widely implemented one in hardware, and Credence. LQD here is the push-out algorithm. Our interest from this plot is whether Credence follows the performance of the push-out algorithm, and that's exactly what we see in our evaluation. Further, we would like to see how the prediction error affects the performance, and the expectation is that the performance gradually decreases as the prediction error increases. And this is also what we see here from the plot as we increase the probability of flipping a prediction. Let's say we start with perfect predictions and we start to flip each prediction. So the error is increasing towards the right-hand side of this plot, and we are looking at the flow completion time on the y-axis. What we see is that when the error is low, Credence and push-out perform nearly close to each other. However, beyond a certain error, Credence gradually decreases in performance. So Credence is still not the end. It's not the best out of the world. There are many more interesting open questions and future research directions to pursue. One of the interesting questions in our perspective is how to practically train such a predictor. There are two ways. One would be a simulation-based approach. We simulate the network, gather the data of a push-out algorithm, and train based on this data. But this will not capture the entire reality. So the other way would be to do this in a real-world network, but we cannot really implement push-out. There are many more such interesting problems yet to be tackled. Understanding push-out operation is also a great research direction to pursue, because if we are really concerned about getting close to push-out's performance, augmenting with predictions, how complex it is, and whether it cancels out by just implementing push-out in hardware, this is yet to be answered. We discuss many more interesting directions in the paper. Please have a look at the paper. In summary, traditional drop-tail approaches are fundamentally limited, and this cannot be improved further, and they have a strict lower bound. We developed Credence, which is the first buffer sharing algorithm augmented with predictions, and we unlock the entire spectrum of the performance between push-out and existing algorithms. We also show that this works out in reality using real-world workloads, and we specifically focus on flow completion times, and much more interesting metrics can be pursued in the future. Source code is available on GitHub, and I'm happy to take any questions now.